Next, let's look at top of page 496, where the book says something that is worth repeating. Okay, now read this at the very top paragraph. While the graph of a rational function will never cross a vertical asymptote, the reason it doesn't cross is because a function has only one value. That's the definition of a function. If it crosses, it doesn't. Well, that's not the only reason. It's also because the vertical asymptotes exist because the function isn't defined there. Okay, you're dividing by 0 or something. So it doesn't make sense to cross. To cross means it is defined. And anyway, so let's continue. It does not cross a vertical asymptote. The graph may or may not cross a horizontal asymptote. That's because horizontal asymptotes or slant asymptotes are talking about end behavior. That is when x goes to infinity. So what it's doing right now is totally free to cross it. Sometimes graph might cross an infinite number of times. It just keep doing this, okay, until towards the end, as x goes to infinity, then it sort of stop wiggling. But it still might continue to cross it infinitely, even as it approaches infinity and start to get close to the asymptote, but still wanders back and forth. And infinitely, it just do it less and less, and like that. And anyway, so that is so, and also, although a graph might have many vertical asymptotes, depends on how many places the denominator goes to 0, the graph will have at most one horizontal or slant asymptote. Now, we'll worry about why that is some other time. This is just something that I want to call your attention to. There will be at most one horizontal or slant asymptote. And also, here's another interesting situation. Look at this f of x. Okay, now this thing is, if for any polynomial, the highest degree dominates the end behavior. All right, because as x goes to infinity, x to the power fifth is so much bigger than x squared that it just leaves it into the dust. And anytime you consider x go to infinity, like down here, whether it's positive or negative, all you care about is the highest power. So f of x, when x goes to infinity, behaves basically like you ignore the smaller powers. So in other words, it behaves like 3x fifth over x, which is basically 3x to the power fourth when x is huge. All right, so that is another point that I should mention. I also would like you to graph this thing, specifically because the book didn't graph it. I don't know why. And please graph this, okay, on the Decimals calculator or some other graphics calculator if you can, and then and look at it. Now, the reason I want you to graph it is because this thing is, the graphing is somewhat tricky, okay? And let me show you my graph. So here is how you might graph this thing. Now, this is in a Decimals calculator, which I like better because there's one form of decimal calculator. I'll remember to put the link below the video, where it's called, I don't know, function evaluation calculator in decimals or something, where they automatically build a chart for you, and you can enter different x values to see what the function look like. I see that I forgot to show actually the function itself, but the function is the one that we just looked at, x to the fifth, and over x to the fifth minus, I don't know, 2x or something over x plus 3. Anyway, that's the function that I want you to graph, and it automatically gives you values. Now this function, if you were to graph it, you most likely will only see a part of it, okay? Just something right here, and you can't find this part. The reason you can't find this part is because you have to change the y value all the way up to 10,000 to be able to see it. That's just, that's what I mean when I say x to the power fifth dominates all the other stuff. So then you can't see the other part unless you change the x values. The y values. You notice the x value is normal, right? From minus 5 to 5, a little more, minus 10. The y value, if you don't make it at 10,000 per square, you will only see a very small part of the graph. To change the values, is what you do is that, let me see. Okay, now I will show you the entire web page, where on the side, this side right here, okay, now notice the side, there's a toolbox thing right here. Okay, so see the toolbox? You click that and this little window opens. Okay, and then you change. Notice there's the x-axis range, which is now set at -14 or something, which is normal, and then the y-axis range. Notice that it goes to 20,000. So what I want you to do is set the x-axis from -5 to 5, or just that too. That's fine. But anyway, you need to set the x-axis as a normal value, which probably means you don't have to do anything to it. And change the y-axis from -10,000 to 10,000. Because the reason is because when you plug it into the values on this side, see this here? See, when I plug in -3.1 and -2.9, the reason I do that is because x plus 3 is on the denominator, which means when x is 3, the function is undefined and it's probably going nuts somewhere. So as you can see, so I plugged in something close to it to see where the function is going, and you notice that at -3.1 is, what is that? Some thousands of value, right? And then at -2.9 is a negative, also in the thousands, which is why I figured we better change the y-axis number here to at least 10,000. And then you can zoom in and out, which is why the value changed from what I entered. But that's the only way you're gonna get is be able to see the whole graph. Otherwise, you'll just be able to see part of it because your camera is zoomed in somewhere over here. Okay, and you have to zoom out, but only in the y-axis. If you zoom in both x and y-axis, then the whole function just collapses into that looks like a line, and you can't tell the difference. So this is extremely important that you learn how to do this. And for that reason, please plot this graph, okay, on the Desmos calculator. But if you don't have access to it for some reason, then please plot it by hand. All right, with this information right here, that should be good. Just plot a few points, right? And then you can plot the whole graph by hand, which in this case isn't that much harder than doing the calculator route. But the Desmos graphics calculator, of course, look prettier than what you can draw by hand, unless you're an artist, of course. So that's that. So next, let's look at the blue box, okay? And read this thing. There are a bunch of details that there's no need to memorize it. I just want you to read it and have an idea, and then we'll call it done. All right. So the horizontal asymptotes have these qualities. The degree of numerator is less than the degree of denominator. That means there's a horizontal asymptote at y equal to 0. The degree of numerator is greater than the degree of denominator by 1. Is remember only bigger than by 1. Then there is no horizontal asymptote, but there is a slant asymptote. And the slant asymptote is calculated by doing division of the top divided by bottom, being the top has higher degree than the bottom. You divide it, and then the quotient, the result of the division, it will be the equation of the slant asymptote. And finally, the degree of a numerator is equal to the degree of denominator, then the horizontal asymptote is at the ratio of the leading coefficients. Yeah, great. So let's that sounds kind of like quite a bit of detail, right? And so we are just gonna look at each one and check the details, and then call it done. Okay. And when it comes to asymptotes, what matters is that you realize they're there, and you realize that they have certain properties, and but it's not necessary to memorize them. They only you talk about them once in a while, but not that common. So so it's not necessary to be able to recall them in a split second. So let's look at example 7 to see how we might use this rule. Okay, we're supposed to identify the horizontal or slant asymptote for these functions. Okay, and then well, all right. First, let's consider A. A is some kind of a function, and you notice that the degree of the top is the same as the degree at the bottom, which is 3, which means that we follow, what did it say about equal? When it's equal, quote, it says horizontal asymptote at ratio of leading coefficients. All right, so therefore, it has a horizontal asymptote, fine. So it has a horizontal asymptote at which is called y equal to, let's see, the horizontal asymptote is y equal to 6 over 2 because the leading coefficients are 6 and 2. So see, right, it says right here, horizontal asymptote at y equal to 6 over 2 or y equal to 3. Remember, anytime you say y equal to something, that's a horizontal line, okay? X, say at y equal to 3 is a horizontal line going through y value at 3. X equal to 2, let's say, is a vertical line. It will go through the value x equal to 2. And anyway, so that's the part A. Next, part B, it has what it is, the second condition. Degree is great, numerator is greater than the degree of denominator by 1. Okay, that part is important. It has to be bigger than only by 1, otherwise this trick doesn't work. But if it happens to be bigger than the bottom by 1 only, then you can do the division and then the slant asymptote will come out. So let me write this down. Okay, so we have to do long division again, or you can do the synthetic division if you wish. But I'm just going to stick with the long division, partly because so far in this video course, I've done long division 3 times and messed up every single time. Okay, so I'm going to do it. I'm going to keep doing it until I get it right the first time. So let's see how this works. So that should be what? X, right? X times x is x squared. So that's x times x is x squared plus 2x, okay? And then do subtraction, that should disappear. Minus 4 minus positive 2, that should be minus 6. Yeah, because we're subtracting here, just like regular long division. And then we need to write down the next thing, which is plus 1. And also, I didn't miss a 0 here, see? Degree is second power, first power, 0 power, and I haven't missed anything. So anyway, continue dividing, that should be minus 6. Minus 6. Okay, 6, that gives us minus 6x, and then minus 12. And that gives us a remainder of 13, right? 1 minus negative 12, that should be 13. Let's see if I got it right. Yes, I finally got it right this time. Look at that. Anyway, so then what is the quotient? Is x minus 6. Therefore, the line y equal to x minus 6 will be the slant asymptote that this thing is looking for. All right, which is what the book says as well. So that's problem B. And in this case, I guess your book doesn't even want to bother plotting this thing to show you what it looks like. And that, which is fine. That is, just be sure that you plot that thing I mentioned earlier, the function on top of this page. Okay, this one right here. And the reason is because that thing is more tricky to plot because of x to the power of 5th. And I want you to practice adjusting the y or x-axis of the graph in decimals or your own calculator, whichever one you're using. It's good practice to know how to do that and also to know when to do it. Okay, if you see something that should be happening but it's not, that means you need to adjust the x or y axis because your camera is zooming in the wrong spot and you can't see the whole picture. All right, so next let's look at example 8. Example 8, we are considering some problem that we looked at earlier. The point is there was a sugar concentration problem where the sugar was 5 plus T, and then the water was 100 plus 10 T, which we established earlier. Okay, let me write that down. Okay, now in the earlier example, we calculated some kind of sugar to water ratio. So that's why we put it in a fraction form. So sugar was increasing at the rate of 5 plus T squared, where T is the number of minutes or something. No, there's no squared. Why do I have squared in here? Let me get rid of the squared. Okay, so sugar is going at the rate of 5 plus T, whereas water is going at the rate as 100 plus 10 T. You might ask, why is sugar on top and water on the bottom? It doesn't make any difference, okay? You can put sugar, because we normally do it this way because we want to know how much sugar is in the water. If you want to know how much water is in the sugar, that's fine too. No law against it, either way, okay? Just make sure that you know which is which. That is, if what's on top is sugar, do not later decide that it's water. Then you're going to be in for it. But as long as you keep track of which is which one is on top of the fraction is of no meaning to anybody, actually. But most people probably do it this way because there's less sugar than there's water. Yeah. Anyway, so we have this fraction, and what are we trying to do? We are being that these two have the same power, say degree one. So then we're trying to figure out that has there's a rule, the equal, right? And a little on the box it says degree of numerator is equal to degree of denominator. Then the horizontal asymptote exists and is the some kind of proportion of leading coefficient. So the horizontal asymptote, just by looking at this, is going to be y equal to 1 over 10. Okay, and so which means that this graph, if you were to plot it as t goes to infinity, and t doesn't go to negative infinity because we don't care about negative time, but as t goes to positive infinity, it will approach it will approach the line y equal to 110. But what does that mean? That means the sugar-water ratio, it will eventually reach equilibrium, let's just say, in physics, and that in the sense that it will be the same. As you add sugar and add water at this fixed rate, sugar at this rate, water at this rate, eventually the proportion of sugar-water will become stable at 110, okay? And because this is how because of this exact rate that you are adding it. So that the beginning part, you started with 100 gallons of water and 5 pounds or something of sugar. That will not affect it. Eventually, this thing will just be 110. That is, the proportion will be t over 10t, which is just 1 over 10. And your sugar to water ratio will be 1 part sugar, 10 part water, if you just keep adding it. And of course, that has a lot of requirements, such as, how big a tank are you getting that you can just keep adding water forever? Let's not think about that, okay? So that's example 8. Now next, let's look at example 9. Identify, that is just, a standard problem, I guess, where we have a bunch of stuff, and we have to, you have to identify the horizontal and vertical asymptotes, if there is one. There are several vertical asymptotes because the denominator goes to 0 several times. At first, x minus 1 equal to 0, which is x equal to 1. Okay, okay, I will actually just maybe talk like this. Okay, so since x minus 1 equal to 0 is in the denominator, so x equal to 1, see right, where's x equal to 1? Right here. Yeah, it might be better if you look at your own book. But anyway, x equal to 1, as you can see, is an asymptote. Similarly, x equal to negative 2, another vertical asymptote. X equal to positive 5, another vertical asymptote. Where the graph, as you can see, cross up one way and down the other. Okay, and then what about the horizontal asymptotes, if they have any? Well, as you notice that the degree on top is 1 less than the degree on the bottom. And what did the rule say again? Let's look back if you don't remember, because I don't. Yeah, the degree of numerator is less than the degree of denominator. Doesn't matter how much. Then there exists a horizontal asymptote at y equal to 0, which is showing right here. Okay, here's a horizontal asymptote. As y equal to 0 is the x-axis, and as you can see, the graph approaches x. The x-axis as x goes to infinity. What was the function again? Yeah, which means the function goes to 0. Okay, that is what approach y equal to 0 means. Because the x-axis is the same as y equal to 0, and x goes to infinity, then the whole function then goes to 0. Now on this side, it looks different. What happens when it goes to negative infinity? It should be the same. Actually, let me check. Anyway, yeah, see, as it says right here, as x goes to plus or minus infinity, f of x goes to 0. So why is it drawn like that? Let's see. That part is probably a bit wrong because the function is only 0 at 2 points, at positive 2 and negative 3, because the numerator is 0 at positive 2, okay, and minus 3, which says it does cross it. Oh, I know, so it goes past it, but eventually it'll approach it. So it has to cross -3. So then it's down here, but eventually it will approach the y-axis. So the graph is not wrong. It's just it can't show you what happens when x goes to -infinity. So you just bear in mind that even though it crossed -3, eventually it'll go back up and approach y-axis. Okay. Yeah. So that should be good enough. Please do this example as part of your homework. And let's go to the next page. Next, let's look at page 498, okay, and where we have the intercepts. Well, the intercepts are nothing new, okay? It's the same intercepts. The x or y intercepts are the same things that we've been doing this whole time. That is the y-intercept. That is when does the function cross the y-axis? It crosses it when x equal to 0. All right. Unless, of course, it isn't even defined as 0, then it doesn't cross it. Assuming it's defined, then the y-intercept is at f equals 0. Now, the x-intercepts are the same as the roots, right? That is when the function goes to 0. The function goes to 0 when, in the rational function, the function goes to 0 when the numerator is 0. Let's look at example 10, okay, to know what this means. Is this the same thing we just did? It looks familiar. Yeah, I think so. But doesn't matter. Now, let's look at example 10 where we are talking about intercepts, which we have already just now seen. Now, the y-intercept is when x equals to 0. So if you plug x equal to 0, plug in all 5 x's, and then you should come up with some kind of an answer. And that would be whatever this is. And yeah. Which the graph is on the previous page in example 9. Well, is it example 9? Well, whatever, we don't care. Okay, so the point is the graph equals to 0.6. I guess if you plug in, that is, if you plug in 0 for the function and then calculate the value, and eventually you'll get it. And then as far as when the function, to find the x-intercept, that means the function itself has to be 0, and you solve for x. In that case, that just means the numerator has to be 0, okay? That's how you solve all rational functions. You turn it into a fraction, and then you set the numerator to be 0, because the denominator, the only time a fraction it becomes 0 is if the numerator is 0, no matter what the denominator is. So then the numerator is 0, then very soon you come up with what the x value is, okay? And then you plot this right here, which is, I believe this is the same thing as the previous example, right? Yeah, it looks identical, and it is. So that's example 10. Please do that as part of your homework. And then we'll go to the next page. So now let's go to page 499 where we're talking about graphing rational functions. So now we've talked about to graph a function, we know where the intercepts are, and then we know if it has any asymptotes and stuff like that, then that should be enough, okay, for us to graph something. The first graph, of course, is the most common graph on this page, the y equal 1 over x, the simplest rational function there is. Now the second graph, I think, is 1 over x squared. Yep, it is, which is fine. And then the third graph, as you can see on the bottom here, that's a little more complicated. Okay, you have a double root, and then and about 3 different asymptotes and stuff. Okay, and so then when you graph it, then well, yeah, then we know there are various things. There is the horizontal asymptote at y equal to 1 because they have the same proportion. So you just calculate the coefficient fraction, which happens to be 1, okay? Both leading coefficients of the numerator and denominator is 1, as you can see at a glance. All the x's have no numbers in front of them, no coefficients. So everything's 1, so y equal to 1 is the horizontal asymptote. And then the stuff at the bottom equaling to 0 means -3 is an asymptote and +2 is the other asymptote. And then, well, knowing that helps you plot it on the calculator. And as you can see, the graph proportions on left and right, it goes 1, 2, 3, etc. But up and down, in the same amount, it went up to 18. Okay, so that's because that's the only way you can graph this thing to make it look reasonably comprehensible. So please graph this yourself as well when you on the graphics calculator. Next, let's look at page 501, okay, at example 11, where you are giving a regular rational function, all factored and nice and good to go, and you're supposed to calculate, to graph graph it, this thing. Now, so please graph this in the Desmos calculator, paying attention to the horizontal asymptotes, if any, or the vertical asymptotes. Now, right now, the degrees are the same, which I think that means there's some horizontal asymptote, right? At y equals 0, yeah, I think that's, or is it? Well, there was some rule, okay, I already forgot what it says. Please look it up and then do the graphs. And it's, as you can see on the next page, the graph comes out very nicely, especially if you do it on the calculator. You mostly need to pay attention to what the x and y axis, the limits has to, how much it should be. In this case, it's just regular, okay? It's 5, yeah, it goes 5 on y, 5 and -5 for y, and also 5 and -5 for x, so you don't really have to do much of anything. And does this thing have a horizontal asymptote? Well, figure it out, okay? And and then and that's that. And the next trick your book wants you to do is you're given some kind of a graph, okay? And you're supposed to write down what the function is. That is that's not as useful of a trick, in my opinion. That practically, when does that ever happen? But I guess it doesn't hurt to learn it. What you do, so let's look at example 12, okay, which is on page 503. And then we have something like this. Now that is, all right, so we have some kind of vertical asymptote at 2, x equal to 2, right? And x equal to -1. So, and then the fact that the asymptote goes both directions means that the x equal to 2 is a double. That is you have to write down the answer as a squared. The exact reason for that is not important. Yeah, see, here's the answer. The x equal to the x minus 2 is being squared because both sides of the asymptote function approaches the asymptote from the same direction. And so anyway, so that's what happens. And then the top is the x-intercept, right? The x-intercept appears to be at positive 3 and -2. And then you need to figure out what the number a is, because all the asymptotes and stuff give you the function, but it doesn't really tell you what the number is. There is a number in front, and you have to figure out what that is. And to do that, just figure out where does it hit the y-axis. That is, what happens when x equals to 0. When x equals 0, it seems to be 2, I mean -2. So you plug it in, set x equals 0, a equal to 2. Okay, and it says right here. And then that will help you calculate the value of a. See, here is the value of a by doing that. And then that, so a turns out to be 4/3, so you plug it in there, and that's your original function. Yeah, that is not a skill I've seen used like ever, but it doesn't hurt to have, okay? It's so please do example 12 as part of your homework and make all this come out. And remember, it's very important to do examples as your homework, especially when you're learning this thing from a video course where basically you're teaching yourself, right? So then doing examples as homework means that if you have any trouble, then you can look up the example and it explains in great detail how it's done. So that works out very nicely. Now, so that is the end of this video. I'm not going to assign any homework in this section because I feel that to know all the details of asymptotes is there's no need, okay? I mean, doing 12 examples is should be sufficient for you to build a reasonable familiarity with asymptotes. And what they are is for rational functions especially, and in the future, there might be other functions you learn that also have similar behavior sometimes. That when x goes to infinity, the function might approach something, or when that's the horizontal asymptote. Or in the case sometimes a slant one, and then the vertical asymptote is special in cases when you have to divide by 0, which happens in rational functions sometimes, but not always. Okay, sometimes it might divide by a bunch of x's at the bottom, but the situation on the bottom doesn't have any real zeros. Okay, like, so then when you divide, you don't have to approach anything. I mean, that is, there's no break, there's no vertical asymptote. For example, if you were to divide, say, by x squared plus 1, if your denominator is x squared plus 1, on top is whatever, x or something, and this thing, you will not have a vertical asymptote because this thing does not ever go to 0. And because you have a squared here, so, and most it will go is, the least value this will become is positive 1. Anything else is going to be bigger. And if it doesn't go to 0, then you don't have a vertical asymptote. So it's not guaranteed that any rational function will automatically have a vertical asymptote. But if there is one, then you know what it means and how it got there. And that will be good enough for this section.